Welcome. My name is Brian Lizon. I'm from the Precision ADC group at Texas Instruments. So today I'm actually going to be talking to you about understanding how reference noise impacts your ADC's performance. And we picked this topic because when talking to analog engineers, a lot of people understand the signal path very well, but they don't necessarily understand how the reference, which is not necessarily in the signal path, affects the system. So I was hoping to kind of provide that information to you guys today. So this is the agenda. We have 3 topics. The first one is just an introduction to voltage reference noise, and again, how that impacts your signal chain. The second section is talking about reducing the effects of voltage reference noise, a couple of techniques to do so. And the final section, if we have time, is talking about some important tools and some other precision ADCs that might be useful for your next design. So the first thing I'm going to do is start with a question in the introduction to reference noise, and it's, does ADC noise include voltage reference noise? And what that means is, if you look at an ADC's data sheet, like this is a table from the 24-bit ADS 1261, a Delta Sigma ADC from Texas Instruments. This is the input referred noise table. And the question is, when you look at this table, does this include reference noise in these measurements? We actually characterize ADC noise in a couple of different ways. This is just one of them. When you look at a voltage reference and how it connects to an ADC, again, it's not always clear how this impacts the signal chain. It's not in the input path. So it's really, is the noise additive? Is it root sum square? You know, how does this work? So the best way to understand kind of how that works, so the first step is to separate this into ideal devices with the noise of each component referred to the input. So that's what's actually showing here. Those circles are the noise of the device, just moved to the input kind of as a voltage noise source at the input of the device and the voltage reference. So the output code of an ADC is proportional to the ratio of the input voltage to the reference voltage, and then the associated noise of each. So you can see that if there's noise in the reference, it's going to show up in the output code in some way. When we characterize an ADC for AC parameters like SINAD or SNR or something like that, we apply an input sine wave, right? And in that case, we have a non-zero input, so this noise from the reference actually shows up in the output code. So in that case, when if you use a testing system, or if your system is similar to the testing system of what we use to characterize the device, you can actually expect to get reasonable datasheet performance in terms of noise. However, for that first table I showed, the input referred noise, what we do is actually short the inputs together and apply a mid-scale signal to both. But again, the input voltage is still 0 volts. So in that case, there is no noise in there is no reference noise showing up in the ADC noise in your datasheet. So in most cases, or in fact in all cases, you're going to have to apply a non-zero input, right? That there's no system that utilizes a 0 input to actually operate. So a real system will always have a non-zero input. So the question then becomes, how does reference noise enter the system and what effect does it have? So the way we're going to look at that, we're going to look at it in 2 different ways, but we're going to use this same, just very simple circuit with an amplifier, an ADC, and a voltage reference. And in this case, these could all be one device. They could be an ADC with an integrated voltage reference and an integrated amplifier, or they could be discrete components. The analysis is the same. And for the first part of this analysis, we're going to set the gain of the amplifier to 1, so effectively no gain. And we're going to apply just a 200 millivolt input signal. So with no gain, the output of the amplifier is also 200 millivolts. So this, again, is the input voltage to the ADC. Assuming just a 2.5 volt reference, you could use any voltage, but for this analysis, we'll use a 2.5 volt. The amount of reference noise that gets passed to the input of this signal chain is given by this formula. And again, this is referred to input. That's what RTI refers to. So this formula actually has two kind of key components to it. The first is the fact that it's scaled by the inverse of the gain. And you might notice that, V out over gain is actually just the input voltage. So again, this is effectively V in over V ref. But it helps to understand this in terms of the output voltage and the gain itself. So what this means is that if your gain was much higher, you would actually have less reference noise in your system. But the more important thing actually is this fact that you have this scaling factor here. The output voltage, which is just the input to the ADC, divided by the reference voltage, is actually scaling the amount of noise the reference applies to the input here. So effectively what that means is if you apply a full-scale signal where your output is equal to the reference noise, you're going to get all of your reference noise at the input. Whereas if you had a 0 volt or anything, a much smaller input voltage, then you would have very little reference noise. And you can see that actually by just applying the numbers we have here. So in this system, with a 200 millivolt input and 2.5 volt reference, we're actually only seeing about 8% of the voltage reference noise at the input of this signal chain. So that's all we're seeing here. And again, this is for a specific full-scale range. But if you applied this, this to all of the different full-scale range options, you'd actually get a plot that looks similar to this. So this plot is actually showing the positive full-scale range of an ADC, everything from 0 volt to 2.5 volt, which is 100%. This is the maximum input signal you can have. And then every 10% increase in between there. So this is actually just showing the positive full-scale range. So the negative full-scale range would look exactly like this. It would just be flipped about the y-axis. But for the sake of clarity, we can just look at this, and the point will still be made. The blue bars here represent the ADC noise. So again, this is from the ADS 1261. At the given settings here, again, there's no gain. And across input voltage, the noise of this device is constant. We're not changing the gain, we're not changing the data rate, we're not changing the input bandwidth, so the noise stays the same. So it's flat across full-scale utilization. The reference noise here, given by the red plot, is actually from the Texas Instruments Ref 6025. This has an output voltage of 2.5 volts. And this system, we're just going to call it now based off of the ADC settings, has a noise bandwidth of 14 hertz. And I'll talk about that a little bit more later on why that's important. But for now, I'll just make that comment. And as you can see, due to that scaling factor, we have this linear increase in reference noise as you go from 0% to 100% full scale. And so the ADC noise and the reference noise, we consider them to be uncorrelated. So we can actually determine the total noise just by doing the root sum of squares. So that's generated, or that's shown by this green line here. So this again would be the total noise of that system I showed on the previous slide. And I want to talk about 3 different points on this plot and kind of how you derive them. So the first point is point A, and that's at 0% full-scale utilization, which is effectively a 0 volt input. And that's what you can, that's the same condition for that, that datasheet table that we saw at the beginning for the input referred noise. So you can actually read that point, you can determine what that point is just by looking at your ADC's datasheet. Point B is up here, and that's where that's at 100% utilization. And that you need to estimate using your references datasheet and the effective noise bandwidth. And the reason you need to do that is this is the output noise spectral density curve for the Ref 6025. And as you can see, it's not constant, and there's no easy way to determine how much noise actually enters your system just by looking at this curve. So you use the effective noise bandwidth as just a cutoff to determine how much of this how much of the area under this plot actually shows up in the ADC measurement. And as you can see, this plot also has a very high 1/f region. It's and a kind of a flat broadband region, similar to some amplifiers. So we actually have some Precision Labs content on amplifier noise and kind of how do you determine how much broadband, how much 1/f is in your system. So you can use those same formulas to determine reference noise. So it's actually a little bit easier to calculate. So again, point B is just calculated using this plot here for this specific device and using the effective noise bandwidth. In general, though, if you're using a high-resolution ADC, your reference noise is generally going to be really high at 100% utilization. So a lot of times you can just estimate this point as the reference noise by itself. Finally, C is just any point in between. And you can use this formula shown here. This is, again, just a root sum of squares. The main difference is it has this scaling factor, and that's the output voltage divided by the reference that we showed at the beginning. So with that being said, we kind of looked at what happens when you change your input signal and hold your gain constant. So what we're going to do now is keep your input signal constant and change the gain and see how that affects the system. So in this case, we're going to use a gain of 10 instead of a gain of 1. All the other things are going to be the same. So a 200 millivolt input gives you a 2 volt output. Reference voltage will be the same. Formula is the same. So what's interesting here is, again, that despite using gain, despite having a larger input signal to the ADC, the amount of reference noise that's passed the system is the same. It's still at 8%. And again, what that means is that the noise referred to the input of this signal hasn't changed despite using gain. In reality, what the gain is doing is helping you lower the ADC noise, but it's having no effect on the input referred voltage reference noise. And again, that's because this input signal isn't changing. It's staying the same even though the input to the ADC is different. But we're talking about reference noise at this point. So if you do the same thing as we did earlier, you hold your input voltage constant. At this point, we're going to call it, it's going to be 20 millivolt approximately, because that gives you 100% utilization at the highest gain. And we're going to sweep the gain of the device, the ADC shown here, from a gain of 1 to a gain of 128. So again, we're going to use the same device, the ADS1261, a very low noise delta sigma ADC at the same settings. And the reference will be the same as well, the ref 6025 with the 2.5 volt output voltage. And the bandwidth is going to be the same as well. So as you can probably guess, doing the root sum of squares, the total noise is going to approximately just be the ADC noise. The reference noise in this case is so low that it doesn't really factor into this measurement. And that's because this input voltage is so small, right? It's not allowing any of the reference noise into your system. So what is the question then becomes, what is the key takeaway, or what is the point of this? And you can actually understand this a little bit better if you look at dynamic range. So dynamic range in this case is what we'd call, what many engineers refer to as ENOB, but was really effective resolution. It's measured in bits. It's not AC ENOB, it's DC ENOB. So it's measured in bits, and we're basically talking about what's the dynamic range, your signal to noise ratio, given the parameters we have in both circumstances. So this red line right here represents the first signal chain we looked at, where we had the gain of 1, and your input voltage was changing. The second plot represents the other one, where the gain was changing, and the input voltage remained the same. It was constant at 19.5 millivolt. So one of the interesting things about both of these plots is that they tend to flatten out at some point. You can see there's a really steep rise for this one, and it kind of starts to flatten out. The same thing here. This one's a little bit more gradual, but then again, it starts to flatten out. And what that point essentially represents is what we call a useful gain limit. So for the red plot here, it happens at about 20.7 bits, which is about 40% utilization. For the blue plot, it happens at about 19.1 or about 25% utilization. And basically what that's telling you is that when you've hit this point, you've hit the maximum dynamic range your system can really afford you. Anything beyond that, you're just going to get the same, you're not going to get any increase. You can increase your, you can increase your gain, you can increase your input signal. It's not going to help you. So you're kind of stuck at that point in terms of dynamic range. So one of the ways we can exemplify that is by looking at this 50% utilization factor for both plots. So in this case, this point here has a total noise of approximately 32 nanovolt RMS. And if you compare that to this one actually has 705 nanovolt RMS. So it's approximately 22 times more noise here. So the real question is, why are you getting more dynamic range at this point with a much higher noise floor? And the reason is obviously because of the input range. The input range for this device, this scenario here is much smaller compared to the noise relative to this. So what's happening is that with this device, or this parameters here, even though the noise is much higher, you're able to take that much higher input signal and cut it into more distinct codes. So you actually get better dynamic range even with a higher noise system, which is kind of counterintuitive, right? You'd always think that if you have low noise, you're going to get the best performance possible. And it's not always the case. And that's, again, in part due to reference noise. So one of the key things here to remember is that if your input signal is small, as it's showing here, what you can do is you want to be able to gain that up as much as you can. Again, eventually you'll hit a limit where it doesn't make sense anymore. It's not going to help your system. But you want to gain that up to reduce your ADC noise as much as you possibly can. Comparatively, when you have much higher input signals, in this case we had an input signal of about 1 volt, you can't apply a gain. Gain's not going to help you in this situation. Maybe you'll get a gain of 2, but it's not going to help you. So in this case, you want to make sure, because you're going to get a really high full-scale utilization, that means you're going to get a lot of reference noise. So you want to make sure your reference noise and your ADC noise are approximately at the same level. You don't want to buy use a very low noise ADC and a high noise reference at that point, because all you're going to see is your reference noise, and you're going to be paying for ADC performance that you cannot actually use. So you always want to make sure when you have large input signals that you can kind of match the performance of the two. And that can help you if you use a higher noise. If you use maybe a 16-bit ADC, then you don't need to use such a high performance reference. There are some cases where you might need to, but in general, that's the case. So even if you do have a large amount of reference noise, there are some ways that you can actually reduce the effects of reference noise in your system. So I'm going to talk about a few of those right now.
현재까지 저희 그 레퍼런스 노이즈 관련해서 설명을 드렸는데요. 저희 데이터 시트에 나와 있는 내용은 이제 ADC 자체 노이즈 레벨이 나와 있고요. 전체 시스템의 그 노이즈 레벨을 확인하기 위해서는 이제 레퍼런스 노이즈까지 포함해야 되는데요. 그거를 이제 간단한 수식으로 계산한 게 그 게인하고 그 ADC 인풋 앞에 있는 그 앰플리파이어의 게인하고, 그리고 그 볼티지 레퍼런스의 볼티지 레벨, 그리고 ADC 인풋 볼티지 레벨 그 연관관계를 나타내는 수식을 보셨고요. 이제 노이즈 레벨이 인풋 볼티지가 높아지면 그 같이 커지고, 게인이 커지면 줄어드는 상관관계가 있는 표로 계속 설명을 드렸고요. 그리고 그 나중에는 이제 그 수식하고 실제로 다이나믹 레인지하고 연관관계에 대해서 설명을 드렸습니다. 그리고 다음으로는 그러면 어떻게 이 레퍼런스 볼티지 노이즈 줄일 수 있는지 그 방법에 대해서 계속 설명을 드리도록 하겠습니다.
Okay, so now I'll start talking a little bit about some of the ways you can actually reduce the amount of reference noise in your system, because this is a kind of a practical implementation of the information we've just learned. So the most obvious way to reduce reference noise is to use a low noise reference. Again, not a not a grand statement, but we have, Texas Instruments has a variety of different types of references. We have the Ref 3000 series, we have the Ref 6000, this is one of our lowest noise. So if you want the best performance, you're going to have to pay for basically the lowest noise reference you can find. But for actual real techniques, one of the things you can do is to decrease the filter bandwidth of your system. So most ADCs, delta sigmas or SAR ADCs, will have an anti-aliasing filter at the input. They'll also have an anti-aliasing filter here on the reference. So as we saw, the filter, the effective noise bandwidth of the system helps cut off the reference noise. So if you move that filter back, you actually allow less reference noise into your system. That's not always practical because the lower the cutoff, the longer the settling time was going to be. But in general, this is one way you can reduce that. However, we recommend on the input to use COG type capacitors. These offer a very low voltage and temperature coefficients. So they have the least amount of noise entering the system. But these tend to be limited to about 10 to 15 nanofarad. So it also just practically limits the amount of the bandwidth of this frequency, or excuse me, of this filter. However, you can use the X7R type capacitors on the voltage reference filters because this is basically outputting a constant DC voltage. So there's going to be very little opportunity for drift. In either case, for the filter resistors, you want to use low noise, low drift as possible. The lower the drift, the more they're going to cost, so you need to balance that with the needs of your system. Generally, we recommend no more than 10K ohm for either filter path, because then the thermal noise of the resistors might actually start to dominate your signal chain, especially for very low noise systems. One of the other things you can do to reduce the amount of the filter bandwidth or the bandwidth of your system is to reduce the ADC bandwidth. So especially for a delta sigma ADC that has a programmable filter inside, you can actually change the bandwidth of your system, and the smaller you make it, the less noise you'll allow into the system. As you can see here, for the very low bandwidth system, this is about a 2.5 sample per second data rate, you get only about 700 nanovolt of noise at full scale. Again, assuming the Ref 6025 from the previous examples. Compare that to 24 hertz or even 96 hertz, and you're obviously getting much higher noise into your system. One of the interesting things, though, and again, another one of the trade-offs you have here is that you have these, this is the point, I've marked the point where you hit that dynamic range limit on each plot. So the smaller your bandwidth, the closer that gain limit is to 0% utilization, which means that once you get to this point with a very small bandwidth, there's nothing, no gain, no changing your input signal, nothing's going to help you actually reduce or increase the amount of dynamic range you have. So that's kind of the trade-off is, you know, this might be a sweet spot here in terms of allowing you at least some variability in your gain and filter bandwidth. So that's kind of, again, kind of the trade-off that you experience when you decrease your ADC's bandwidth, is that you tend to lose some of the value of your gain and, you know, gaining up your input signals. One of the other things you can do, and again, a lot of times in your systems, some of those parameters are fixed. Your input voltage, you don't necessarily get to decide. It usually comes from a sensor. You have to measure that sensor. Maybe you can decide the excitation voltage, but a lot of times that is fixed. Sometimes you have settling time requirements, so you can't change your filter cutoff and things like that. So the last way you can kind of change how much reference noise is passed into your system is by choosing an appropriate reference configuration, whether it's internal, external, or ratiometric. So this is just showing an internal reference. So the ADS1261 actually includes an internal reference included inside the device. It's about a 10 ppm per degree C max reference, so it is pretty good. It offers good performance for most applications. The main advantage here is that it obviously reduces your PCB area, it reduces the amount of power consumed, and it reduces the cost of your system. If you don't need another discrete component, then it reduces all of these important parameters for a system. However, relative to an external reference, the internal references generally have higher noise, and they have higher relative drift. So again, if the internal reference is not enough, is insufficient for your application, you can use an external reference. The ADCE1261 also has external reference pins. So you can apply an external reference, and that's what we did in the case of a lot of these examples, is we applied the Ref 6025. The advantage, again, of an external reference, in most cases, it has lower reference noise and lower drift, but that comes at the expense of higher power, and that's kind of one of the ways this lower noise is generated, is kind of by burning current. It does add cost and board space. It's another component you have to place on your board. And the last thing is that the reference noise and the ADC noise are uncorrelated at this point. With an internal reference, the ADC and the reference share the same die, so you can kind of assume that they're not going to kind of drift in opposite directions. In this case, you can't really make that assumption. There are cases where it can drift. They can drift in the opposite direction, which results in kind of a worst case scenario. So that's one thing you might have to look out for as well. The last one is a ratiometric reference. And this is kind of something that some people might not have seen before. But this is when sensor biasing, or excuse me, sensor excitation is necessary. So in this case, there's a resistive bridge right here. And the resistive bridge is excited with this 5 volt voltage. So instead of using an external reference or an internal reference, we actually route the excitation voltage, the positive 5 volts and ground here, as the reference. So if this voltage changes, if it starts to drift up or drift down, the reference drifts the same way, in the same direction. So if you go back to the very beginning, the output code is a ratio of the input voltage to the reference. So if those are drifting in the same direction, that noise effectively cancels out. So this is actually the lowest noise reference configuration you can use. And the downside to that is it's only possible in certain situations when you need sensor excitation. So this is an example of one of those. If you need to buy or excite an RTD, that's another example of where you can use this ratiometric reference. But it's not able to be used in all circumstances. So if you can use it, we recommend you do. But again, if you can't, then you have to choose either an internal or an external reference. And we've talked about this effect kind of qualitatively so far, just saying one is better than the other. This is actually a plot from the ADS1259 datasheet. So this is a 24-bit delta sigma ADC. So these are actually measurements taken using the 3 different reference configurations. So this plot here shows an internal reference, the internal reference of the ADS1259. And as you can see, at full scale, you're getting about 400% increase in noise compared to just the ADC noise by itself, which would be approximately at this 0 point here. If you look at the an external reference, in this case the Ref 5025, you can see that you're still getting a sharp increase in noise. It's not as bad as the internal reference. It's about 150% increase. And finally, with the ratiometric configuration, you only get about a 50% increase in noise compared to the ADC by itself. So as you can see, qualitatively and quantitatively, the ratiometric configuration is the best one to choose. So throughout this presentation, I've talked almost exclusively about high-resolution ADCs. This is a 24-bit. The ADS1261 is a 24-bit ADC. So the reason I chose those is because a little bit of reference noise is very apparent for a 24-bit ADC. But the question becomes, does this matter for an 8-bit ADC or a 16-bit ADC? So what I'm going to look at right now is kind of where that cutoff is as far as when reference noise really does matter. So if you look at this table here, we have the ADC noise. This is in millivolt RMS for all these different resolution, ADC resolutions. For the 8 through 16 bit, it's approximately just quantization noise, or LSB size. That's what dominates this, this noise value. At the higher resolution ADCs, it starts to get into the thermal noise. So these are actually taken from specific ADC data sheets. So if you're able to apply a reference to all of these, it's not always the case, but theoretically we're going to assume that that's possible. And you calculated the total noise for that system. So this column right here shows the ADC plus reference total noise. So again, for an 8-bit, there's almost no change because the ref 6025 adds almost no noise. And again, this is at 100% full scale. So this is the maximum amount of reference noise that can pass into the system. And this reference, you can't even see it. And this final table this final column just shows the percent increase in noise compared to just the ADC by itself. So again, if you look at the first 5, the low resolution ADCs, you can see that reference noise has almost no impact. The ADC noise is dominating by far for the first 5. So even using a low noise reference isn't helping you in any way, shape, or form. However, if you compare that to the high resolution ADCs, you can see that at 18 bits, you get about 8% increase, not bad. But at 24-bit level, you're getting 150% increase. And then we have a 132-bit ADC. At that level, you're experiencing almost a 600% increase in the total system noise when using the ref 6025. So the key takeaway here is that there's kind of a cutoff for when reference noise matters in your system, and it's approximate at the 16-bit level. So a lot of ADCs at this level don't actually include external reference voltage inputs. For this reason alone, it's just not going to help you. A lot of times, it's just the reference is derived from the ADC supply. So if you have at least a reasonably noise-free supply, you can expect to achieve 8, 10, 12-bit performance. It's really at this level, at the high resolution level, where you really need to be concerned about reference noise and making sure that you're following the guidelines that presented today, using the appropriate reference configuration, and using the other noise mitigation techniques. So the last thing I want to talk about very quickly, so a lot of the stuff we talked about today has been very theoretical. These are just some tools, pieces of collateral that can actually help you kind of design your system better, faster, easier. So I believe Lenny Lee actually touched on Precision Labs. So the information I presented today will actually be a Precision Labs module in the future. I won't go into more detail on that since he already explained this to you. The only thing I will say is that we have these, the Precision Labs curriculum actually comes with, or you can purchase a board. There's one for the amplifier section, there's one for the ADC, so you can actually do a hands-on training using the material you've just learned in the Precision Labs modules. So this is, again, a very high value piece of collateral. It's perfect for beginner engineers, it's perfect for advanced engineers. Wherever we've taken this training in the world, it has been met with a lot of positive reactions, again, wherever we are. So this is something you can check out. There's a lot of information. I would recommend looking at it. One of the other thing we have is the Analog Engineers Pocket Reference. So this is kind of a cheat sheet, a lot of just fundamental information about analog signal chain design, things like talking about op-amp bandwidth instability, some A to D or D to A conversion techniques, how do you convert hexadecimal to binary, things like that. Just very fundamental information. It's available as a PDF, actually as an iPhone app, and there's a hard copy, an actual book. So you can actually purchase this from ti.com, and it's a lot of very useful information. The same people that created Precision Labs actually created this. Very, very experienced analog engineers. So again, it's really high value information. Costs about $5, or you can download it for free at ti.com. We also have these circuit cookbooks. We have ADC and amplifier circuit cookbooks. So what these are is this is just showing these kind of generic circuits, you know, for maybe how do you convert high voltage to low voltage, like an attenuation stage, or single-ended to differential input. It's a very generic circuit. It comes with schematic diagrams, SPICE simulations, and you can take these and apply them to your specific application. So it's a very quick way to adapt a very simple circuit to what you need it to do. And there's a lot of these right now. I think there's about 30 or so, and we're adding more all the time. And again, this is available for free at ti.com. There's also one for RTDs and thermocouples specifically, so you need to measure that. There's a lot of different ways to do so, so this just takes you kind of step by step through that process. And the last thing I'll say is I think Lenny also brought up the E2E page, our support forum. So our applications engineers speak directly to you and provide support. One of the key things here is we actually have an FAQ page. So this is where we keep a lot of our, often or again, frequently asked questions, things that come up over and over again. So we put a lot of this information on this page. So this would actually be another source of collateral that I would recommend you guys check out in addition to using the E2E forum. So that's all I have.